Factoring an expression as the difference of perfect squares. Your learning target. You will identify and factor polynomials with two terms into the difference of perfect squares. The essential question is, how can I look for and make use of the structure of an expression to classify it by type? We'll start with a multiplication problem. If I were multiplying x plus 2 times x minus 2, I would set it up with one of the factors as the base of my rectangle and the other one as the height of my rectangle. So I have x plus 2 as the base and x minus 2 as the height. I would multiply my two linear terms, my x times x, to equal positive x squared. Now I can multiply my x on the bottom times negative 1 on the height to give me negative x and another negative x. X times 1 is x, and negative 1 times positive 1 is negative 1. And if I had these algebra tiles in front of me, I would notice that there is a zero pair there with the negative x and the positive x. There's a couple of zero pairs, so I would remove them from my workspace, and my product would be x squared minus 4. So what I want to do is take a look at this multiplication problem, and I want to pay attention to the fact that the x squared minus 4 has an interesting structure. The first term is a perfect square. The second term is a perfect square. And there's a subtraction sign separating the two terms. So next, I want to make use of the structure and generalize. How would I factor an expression that meets that has that structure? So to generalize, when I have one perfect square minus another perfect square, I factor it into a product where I have the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. Now it doesn't matter if the plus or the minus comes first because of the commutative property of multiplication. It just is important to note that you will always have one plus and one minus in my factors. So let's take an example here, and we'll factor 25x squared minus 49. Does it meet the three criteria? Is the first term a perfect square? Yes. Is the second term, 49, a perfect square? Yes. And is there a minus sign separating the two terms? Yep. So it factors into an expression that looks like this. And I take the square root of the first term and I put it as in the first slot, if you will. I take the square root of the second term, and my work is done. I have factored 25x squared minus 49. Now let's factor 9m squared minus 16t squared. This also meets the criteria, so I'll simply take the square root of the first term and the square root of the second term. Now I wonder, is d to the 10th a perfect square? Even though the exponent 10 is not a perfect square, is this expression a perfect square? Well, d to the 10th could be written as d to the 5th times d to the 5th, so therefore it is a perfect square. And I can generalize that any term with an even exponent is considered to be a perfect square. So that will help me factor some expressions with exponents that are even. So let's practice this. We'll factor 100x to the 6th minus 81. So does this meet the structure that I need when I use the difference of perfect squares? Well, the first term is a perfect square because 10x cubed times 10x cubed gives me 100x to the 6th. The second term is a perfect square, and I do have a minus sign separating the two. So I can just put the square root of the first term here in both places, the square root of the second term, and I have successfully factored that expression. Do another example. 49m to the 10th, that is a perfect square, minus 64t squared. So this factors into the square root of 49 m to the 10th would be 7m to the 5th. The square root of the second perfect square would be 8t. Okay, so here's your little exit task. Just put the video on pause and double check when you're done that you have factored it correctly. So both of these terms are perfect squares, so I can use the difference of perfect square technique to factor. I get 11x minus 9y to the 5th times 11x plus 9y to the 5th.